So we'll go over a very few, like a very basic concept right now. Okay. So if you are given an integer of arrays that returns true if it appears twice. So so the thing that we can do with this is um, a few different types of solution, right? So what can be one of the solution that you can use? Anyone? Just a brute force solution. So anyone got an idea how we are going to do this? So in terms of brute force, you guys have heard of that, right? Brute force solution. So it's just a basic solution, right? So if I am trying to given an integer of array, it returns 2. So what I will do beginning is I will try to check 1 with 2, then I'll check 1 with 3, and then I'll check 1 with 1. Okay. And then I will find there is a so there is an appearance of 1 twice, so I will return true in this sense, right? And then so what happens is, so in times of okay, so in terms of a time complexity, what we have done here is you are using O of n. So you guys know O of n? Anyone seen this terminology? I believe you have done seen this, right? Anyone can give me an answer?
Yes, ma'am, we know about
Sorry. So
yes, ma'am, we know about
O of n. So what does n represent?
Like it represents the number of times we have checked with the other numbers.
Yeah, it's mostly the length of your array, right? So it's basically the length of your array, right? So length of array. Okay. So so this is your uh, so this is your time complexity. However, what do you have is as a space complexity? So space complexity is you will have, we are not using any extra space, so we can have a smaller space here, right? O of 1. So the space is not bad, but the time complexity is O of n. Now, if I am trying to now check 2, right? I have to check 2 with 3, 2 with 1, 2 with 3, 2 with 1, right? Then I again add another layer of time complexity. And finally, my complexity value kind of goes over what? What is my complexity value then? N squared, right? So now I just wanted to link back a little bit of you thinking that when I'm also training a very big model, if I am trying to check it like this, like in a brute force solution, then what happens is my time will increase, right? My time will start increasing when you're training it like this, right? Through a lot of for loops, right? So your time complexity starts increasing a lot, right? So you can do what else can you do? So this was my brute force solution. So I wouldn't want I definitely don't want my neural network training pattern to go like this, right? It will, because I have a lot of data, and if I keep doing this, it will just keep increasing my time. Right? So now let's think of another method, sir. So let's think of another way. How can you do another way of implementation? So this was my brute force, right? The brute force solution. Okay, I wrote it already, I think. But what can we do another way of doing this? We can sort, right? So if you are sorting this, what happens is we have 1, 1, 2 and 3, right? So then then I only have to do I do only have to compare only once, right? So I compare this one only, right? And then my time complexity in this situation will become On, and space complexity still remains O1. So do you think I'm saying this right? My time complexity is On. Do you think so? Think about it. I did a sorting and then I'm checking. So is time complexity still remaining the same, On, or what happens to it? Any clue? No? Anyone? Okay. So so do you guys know? Probably you have already heard of this. So let's say we are doing a merge sorting, right? So someday we'll go over this, but because it's a deep learning class, I don't want to go much into that. So this is a time complexity. So this is the time complexity when you have a merge sort. Probably I'm saying it wrong. Think it's the binary sorting. Anyway, so this is the complexity we have. So when you did a sorting, you already did this complexity. On top of it, you are actually using an n. Just forget about that. So this one was for my first sorting, and then I am adding an on top of it, and which is kind of making it in log n, right? So again, if I see that this is not really again a good solution, right? So we did decrease it. So we were able to decrease it a little bit, right? So it went from on squared to on log n, right? But still there is a time, quite a bit of time complexity, and we have a leverage of the space complexity because it's still O of 1, right? Now, what else can we do? So we need to think of a better solution, because here we are not doing anything about the space. So space we can still increase, right? It's still O of 1. So we might have to leverage a little bit of space, like give it a space of On, and then in that way we can decrease a little bit of this time complexity value, right? So what we can go about doing is creating a hash map or hash set. Okay. So that's one of the reason when you are doing an embedding kind of problem. So you already have a character set or predefined character set. So we'll discuss about it today in the transformer class actually. So you already have a predefined hash map actually, or some character set, and then we can use this hash set really well to have a time complexity of On and use a space complexity of On also. Okay. Okay. So let me go over this, and then so then where were we? We would have, so now, so the first goal is um, 1, 2, 3, and 1. So what we do is we are going to put this inside my hash. Right? So it goes 1, 2, 3, and 1, right? Sorry, not the 1, because we are first checking if there is an hash already present. If not, then we input it into the hash set. Then we check, do we have 2? No, then we input 2. If they have 3, we don't have 3, so we'll put the 3 there, and then we have 1. It's a repetition, so we don't have to put it, and we can return that this is already present, so it's 2, right? So we have a duplicate. So when we are inputting this, so my complexity, so for each of these pairs, so my complexity remains O of 1, right? So we are inputting this integers, it's O of 1, right? And then if we are and then if we put this sorry, and then y O of n is my space complexity. So this is my space complexity. Why? Because I probably have to create, so it can go n minus 1 for this situation. It's not going until n, but up until n minus 1, right? But we do have to leverage a hash set of size. So we have to leverage a hash set of size 1 cross n, right? So that's the reason it became O of n. But what happened by increasing the space complexity to O of n, you were able to decrease the time complexity to O of n, not and not O of n squared, right? The brute force solution. Okay, so that's one of the way that you can always think is GPU concept. So GPU concept is giving more space or using more GPU, right? So I think you guys are already training those LLM models, and I will. There is RNN, I think RNN music generation, but I will provide the actual solution to you, which you can run and check, and then make some modifications to it. Okay. So, but you can definitely use those. But when you are using it in your GPU, so you are actually segmenting out. If you are using more GPU, let's just call it one GPU, let's say for now. Okay. So one GPU space, but if you are using more GPU space, you can actually, with this kind of hash set, you can use some more GPU space or CPU space, for example, and then you can decrease your time complexity factor. So it's not a very nice diagram, but I think you guys got this idea, right? Okay. Any questions on this? Does it make sense now? Why you need to have a good solution, or whenever you're writing your code, you also have to think of your data structure situation, right? So that your time complexity doesn't go too far, and then the space complexity also you can leverage it out a little bit. Okay. So any question on this? No? Yes?
No, no.
Okay. Okay. So so then I have another problem. It's the same problem. So this is my solution. Let me just put it there so you can have a look. It's a very simple solution, so nothing complex over there. So just put the solution there, and then take few minutes and tell me how you can, if you probably have solved this. Okay. So given an array of integers, so let me copy this. Okay. Okay, so given an array of integers, integer numbers, and an integer target, return indices of the two numbers that they add up to a target. So, for example, if I think you have already probably seen this problem. There is well-known problem here. Okay, so let's see what can I put here. So 2, 1, 2, 1, 3, comma 5, and then let this be my target. Right? So my target is 4. Okay. So how do you think you can solve this? You don't have to write the code right away, but I just gave you an idea, right? So how can you do this? Probably with hash map maybe, or hash set maybe.
How do I use the map method and iterate through it? And
Mm-hmm. So
and
you
after that you can, yeah.
and after that, what can you do?
Yeah, so like you can just iterate through the map. So like you just give the nums and they give the target. And suppose you iterate through the num,
Uh,
and then after that you can just give a variable where the target minus the num, and suppose the variable a is having target minus the num. So if a is in the num map, so then it's basically you can just return the num map.
yeah. So
And
go ahead, go ahead. Yeah, please go ahead.
yeah, so then the map is equivalent to I, which shows the index of the current position.
Mm-hmm. Okay,
So
and what does complexity become? So the space definitely is
we'll
ON,
yeah, so on.
and then how is your time complexity going on?
Same one.
ON, right? So
Yeah.
you are trying to hang on. So 1, 2, 3, and 5. You are going to put this. That's what you mentioned.
Uh, yeah, correct.
Okay, okay,
And
and
then
then
yeah,
and then you are going to check, right?
yes.
Okay. Okay, I will also provide my solution a little bit later. Just hold on to that thought. I will put this solution after this, just end of this class. Okay, so thanks for that. And now we will, yeah. So now I think you can now kind of understand that why these things are important. And then, yeah. So now let's go into the topic for today that I wanted to discuss. Okay. So everyone have access to this, I believe. I already have. Okay. So so how do I say? So all these language models that we have today are based on called sorry, what do you say? The unit of these structures are called attention, right? So let's just dig into how, because I was trying to describe RNN, which I didn't complete, but I will go back to it some other time, maybe next week. But the thing is that how do you know, or how can you do this sequence type of modeling? So in sequence modeling, there is a problem that as the sequence get longer and longer, your model doesn't. So in uh, do a little bit discussion here. So we had like hidden layers, right? So we would have hidden layers, and this one should be provided all these values, right? But your sequence, for example, if it becomes really long, then it actually causes a problem, right? So this layer, for example, H2. has to remember all the previous kind of layers, right? And so one of the thing that happens is called gradient explosion. So these, when I'm taking those derivatives, right? So the derivative of these gradients, or in the Bragg propagation, right? So of this of x, right? For example, or whatever, like these, we are taking this gradient values. And if I have a very long list, and let's say one of the gradient value was 1 e to the power minus 12, a very small, very close to zero, and then we are kind of multiplying all these gradient values. So what happens at age of 0, you probably will land up at very low gradient or vanishing gradient, vanishing gradient problem. Or sometimes these gradients might be really high, like dg equals to, let's say, 10 to the power 12, right? Very high, and it, you just shoot up it to the sky, right? And it will, your kind of neural networks becomes very unstable. So this is sequence model, but uh, sequence model is good at up to certain point, but when you keep having these kind of problems, you go into the same kind of sentences of language model, you try to put it into now attention layers. Okay. So this is a very famous paper. Of course, everyone, whenever they start, they will show this paper. I think right now it's the most cited paper right now. So attention is all you need. Is so they came up with this kind of architecture in 2017, and since then Google and everyone, like your chat gpt, everyone, every language models, Claude, anything, right? DeepSeek, anything is using all these this architecture. Okay. So this architecture, why is it quite important? Because that space thing, right, which I was trying to mention to you, right? So you can, because if your model goes very big and you cannot handle in one GPU space, so if you try to check a GPU, so let's connect to a GPU. Okay, so let's see. Then I can show you that value. Yeah, and then let's see. So see, the current GPU space is around 15 GP, right? But it's good for these kind of models. But when you have millions of data like points coming in, it definitely is quite difficult, right? So you have to increase your space memory, or you have to increase you have to use parallel RAMs, right, to train your model, right? So and your matrix multiplication, because by this time you understand that most of your calculations are actually done through a lot of matrix multiplication. So the matrix multiplication needs to be divided, right? So this architecture is very good in parallelizing or using multiple GPUs at the same time. So that's the reason it has become very famous ever since it was invented by these researchers. Okay. So today I'll try to give you a small kind of overview, and we might have to continue this a little bit to understand more. Okay, so this is your equation. So up till now we were using the hidden layers, basically the hidden layers, which were getting embeddings of our language or music or anything like that, right? But here we have the same concept, but we are not using these hidden layers anymore. Rather than we are using three terminologies, which is Q, query, K is key, and T is oh sorry, that is my bad. It is not T. It is V. Sorry, did I write that? Hmm. Okay, so I have to yeah, clean this up later on. I'll clean this up. So uh, query, key, and value. So the main three things that we have to think of here is query, key, and value. Okay, and then they are done. Then we have a matrix multiplication, and then we use a softmax over it to get a value. Okay, so the equation might right now seem a little bit intimidating. So now we are trying to break it up. So again, going back to the order, how RNN is working. Okay, so let's think of a situation where my RNN or my sequence model is asked to do a what do I say? Um, is asked to do a machine translation. Okay, okay. So it's asked to do a machine translation. Okay, so this is an example of using a machine translation. So what is machine translation? It's basically like I'm trying to convert this English to French or to any other language for that matter. Okay. So if I'm trying to maintain an order, so how do these problems occur? How are these problems occurring? Is because the order in which my English, the European Economic Area, is not going to be the same thing as the French La Zone Economic European. Okay. So the order will change, and so that's one of the reason. The if it's done a linear mapping, will definitely go into La, but European will go to zone. Okay. So then it act completely fails over here because the ordering is not right. So these are situations when if I'm trying to use a sequencing. Okay, because sequencing doesn't have a positional value. So sequencing, we are only trying to use embedding values. Okay, and then size mismatch. So the is la and European. So this a number of token size, the token size increases, economic becomes economic key. So this is a longer token, right? So these kind of problems to arise. So literal translation from English to French is really getting difficult. Order mismatch, size mismatch. So these are some of the things that RNN cannot definitely handle it too well. Okay. And if it's handling, it's actually losing some information. Okay. So that's the reason in 2015 encoder and decoder architecture came in. So encoder and decoder architecture, one of the most important, according to me, was UNIT, which is used a lot of times in vision modeling or vision segmentation modeling. Okay. So, but that is also used for your um, this kind of machine translation. So rather than using RNN as it is by itself, what researchers started doing is using an encoder and decoder architecture. So in an encoder architecture, they would have a vector representation of the word. So you use an RNN encoder and you do a vector representation of that word. European again same thing, economic area. So you try to do a vector representation of the word. And what the decoder architecture does is it keeps an so it keeps a weight or attend to the inputs. Okay, so it actually realizes that la is actually even though it's taking those values from your what do I say from these encoded representation, it's actually kind of also keeping a track of the position, that the first word is not the first is still the first word for French, but the second word is the fourth word for French. Okay, and then the third word, and sorry, this should have been second word. So like that, right? So these are few things that these are the things positional tracking, and what is or how much do I have to attain to the input. So how important is the European connection with law and things like that. It's trying to keep a track of it. Okay. However, it's it still didn't do a very good job because it's still trying to look at it very sequentially. Okay, so that's one of the reason it was losing some context, right? So how important is particular concept to another concept? So it started losing some context like that. Okay. Um, so any questions until this? No? Okay. So now, give me a minute. Why is it okay. So I'll take 2 minutes break. I'll just more convert this to a PDF. Just, um, because it's really annoying to see this kind of problems happening. Okay. I think I can start sharing again. Okay. So where will be? I'll make sure to provide the PDF version of this. Okay, so we did speak about machine translation, encoder and decoder. Yeah. So now comes your attention. So even with that, it was not giving very good results. So that's the reason they invented or they worked on this attention kind of structure. Okay. So let's say we have a very simple sentence called, which is pizza is awesome, great. Okay. So, and then EOS is end of the sentence. So we usually use tokens to end the sentence. Okay. So EOS is a token that is always used to mention that this is end of sentence rather than a full stop. Okay. So when you are using deep learning kind of architecture, EOS and some other characters I kind of use for this. Now, as I was mentioning in RNNs or any kind of language models, you need to convert these to some embeddings, right? So word embeddings. And do anyone remember what is, or anyone knows what is word embedding? Can anyone mention that? Any idea of word embedding? No? Okay. So let me also try to draw this. Now that was it here. Okay. So, so I definitely believe most of you know this, but you're just not, uh, maybe not confident enough. But I think you all have an idea of what they're getting, right? So if you have a king or a queen, so in a vector space, so king or a queen, let's say, so this is a queen, this is a king, right, or a male, female, right? So male, female, right, for example. So in an embedding space, queen, king, male, female, they they are represented by a vector. Okay, so they are represented by vector point one, point zero zero, point zero two, whatever. Okay, and maybe the king is also represented with point zero 0.01, then 0.0, 0. Maybe just 2 1 because they are very close to each other. So king and queen represent the same kind of royalty, for example, and they are very close to each other in an embedding space. Okay. And then let's say male and female, so point zero 0.03, point zero 0.09, 0.0. Okay, and they are two different, so they are representing gender, right? So maybe they lie very close to each other. It's point zero 0.09 and zero 0.1, for example. Okay. So you can see that this can be all represented by a vector. So in an usual situation, uh, or in most of these language models, these are basically represented by 512 kind of vector values. So they are represented by 512 vector values, and then um, yeah. But for this purpose, we can definitely stick to two, right? But you can already see that to represent one word, we have to use 512 vectors, right? Because that's a very big vocabulary size, and you do have to have a lot of variability to this and things like that. So you usually use 512 for this embedding. So now moving back, you have so that's here. Okay, so pizza is awesome, great, right? So pizza, for example, will have a word embedding. Let's say for this purpose, we're thinking all of these word embeddings have a value of zero point 0.1. So they're just simply represented with one dot or 1 point, right? So 0.1, 2.13, 3.14, 5.0, so things like that, right? So all different words are represented with only one. So this is just an representational purpose, but you have to remember that in actual scenarios, it will go until 512, right? Or even bigger. And then we also need to know a positional embedding. So why positional embedding is important? So see these two sentences. Tom eats pizza and pizza eats Tom, right? So these when you have this sentence, right? So these two sentences have entirely different meanings, right? So if you say Tom eats pizza, that's good, but pizza eats Tom, that's definitely not possible, right? So that's not a possible thing to happen or a phenomena to happen, but it you can still write it, right? That's not a problem. So how would you make your model understand this, right? So if you this was your RNN, so RNN would get confused, right? So Tom eats pizza. This is a sentence or this kind of sentence. It will be trained most upon, or it might get most of the training sets like that, right? So someone eats pizza, right? But pizza definitely cannot eat Tom, but it can still happen, right? So this is where positional embedding comes in. So we'll not discuss much about it, but we'll keep the values of position. So Tom here gets a position of 0, and here it gets a position of 2, right? In your array space, let's say, right? So that's how your attention mechanism knows that where it is located. So how transformers so this is how your transformer establish relations between words and uh, give some attention to the words that are more closely related to each other. Okay. So all of you do have an idea of what is dot product, right? So just in your space, so in your so going back to to one more. So so dot product, so you can definitely, so if you have two vectors, right? So you have two vectors and you just multiply like a vector dot b vector, right? And then you can, so that will give you AP, right? Something like that. That's your kind of your dot product. And it doesn't, then it doesn't actually give you any direction, but it gives you some value, right? So 1, 2, 3, whatever, right? So that's what actually going to happen is all of these positions or all of these um, embeddings, you are going to consider it as a vector space, right? So you're going to consider all these things as a vector space, and you are going to take some dot products between them and find a cosine similarity. Okay. So how similar are these to each other? Or just multiply and check how similar are these to each other. Okay. Now, let's go over to this example. The pizza came out of the oven and it tasted good. So where so uh, it is actually this is a little bit misnomer kind of term, or it's a little vague, right? The position of it, but it's still a sentence, right? So it can refer to an oven, it can refer to a pizza, right? Now oven cannot test good, pizza will test good, right? So this we understand, but how will you make this machine understand this, right? So that's where you will put more value or more importance of the relation of it and pizza over the relation between oven and it. So you will have, so how do you think it's in a mathematical term? So so the dot product value between pizza and it will be much more bigger or larger than compared to the dot product value between oven and it, right? And that's how transformer knows that this relation, so this relation you were not able to do it in a sequence model, has much more attention or much more weight than this and this relation together. Okay. So this is how you do attach an attention to the transformer, right? Okay, so a transformer uses it like that. Okay, so let's talk about self attention. Okay, so in self attention, so the first step is getting an how do I say that? Getting relation of these sentences to itself. Okay, or like multiplying a vector space for these sentences by itself. Or so that's called as self attention. That's the first basic attention mechanism. Then followed by cross attention. We'll try to stick to self attention for now. So what happens is you pick a number. So this is where the ON type of complexity comes in. So so you are picking this number the, and you are trying to kind of model it, or trying to check the, how do I say, check mm, the similarity score. So how well is the pizza related, how good is the similarity or the relation of the pizza, the came, the out. So you have different values for different numbers. So if the is actually multiplied with different numbers, then it will give you different values, right? And based on the context, right, whichever has higher probability of appearing, so that will be given much more weight or much more attention at the end. Okay. So the self-attention calculates the similarity between the and all the words in the sentence. So if I say we are calculating a self-attention, so this is what is happening. It's calculating all the relations between the and how the all the words are related to it. Okay. So then what happens is now, so that's good that we understood how it works. Now, if you have a lot of examples, so now uh, this was one example, but when you are giving it millions of examples, right? And then, so now your question would be, how can you know that you have to give a higher weight to pizza and it, the relation between pizza and it, rather than oven and it, right? So because my model or my data set might have a lot of examples that's related to the, that has a relation between pizza, test, and eat, right? So that's how it knows that when you have a test after it, so when you have a tested or a test token after it, then it's always referring to pizza and not referring to oven. So for some reason, if you had it tasted good, or it was hot, right? For example, something with oven, right? So then it understand it's not referring to pizza, but it was referring to oven, or it is rusted. So pizza is not rusted, but an oven could be rusted, right? So that's how, so this is how your with your increasing epochs of training, your model tries to understand which are more important to each other, and starts giving more importance to those kind of relations with it. Okay. Okay, now finally, let's try to conceptualize this. Okay. So we'll conceptualize this and we'll stop today, and then next week I'll try to implement how the matrices implementation can work on that one. Okay. Okay. So again, I will change this. This is really bothering me, but anyway, let's just think that QK, query, key, and value, and then we have a softmax. So what does softmax do? Anyone? Hello? Any idea what softmax does? Okay, so softmax was is actually used to bring the value between 0 and 1, right, or scale it properly, right? So that's where you try using a lot of softmax. You use softmax layers, right, or a softmax over your layers. Okay, so now let's say Q, K, and B in terms of a database architecture. So you have a last name and a room number. Okay. So let's say we have few last names, and we can assign a room number based on that last name. So we have Smith, Thomas, Smith, and last names like this. And if that person comes in with that last name, so they will be assigned to that particular room number, right? So, for example, let's say there's a receptionist, and you ask, and someone has a last name Sumit. Okay. so which is very close to the query, which is very close to this value. So you are sending a query to this database, and the database, based on the of the spelling of the last name, it's trying to check which will it's closest to which value. So it's closest to this value, and then you get a value of 202. Okay. So then it gives you, then so the database tells you that assign the room number 202 to this person, because his or her name, last name is very close to uh, Smith, right? So then assign 202. So this is exactly kind of the situation that query key and value will actually um, um, uh, related to each other. Okay. So let me give you one more final example of a query key and value. Oh, sorry. Okay. So I want to give you one final example before I close the call. Okay. Same problem. Okay. So let me write it again. Teacher. Okay. So if I have a sentence like this, so what are my adjectives over here? If I have a sentence like this, so what is the adjective and noun that I have here? So I'll just try to give you a little bit easier, or again, a different way of interpreting your attention. So fluffy blue creature roamed the verdant forest. So what do you think would be my nouns, and what will be my adjectives over here? Anyone?
Noun is the creature and fluffy blue is the adjective.
Noun will be the creature, right? That's a noun. And forest is also a noun, right? And fluffy blue will be your adjective, and verdant will be your adjective, right? So fluffy blue creature, and verdant is yeah, let's consider this is also kind of an adjective which is modifying the forest, right? Okay, so now the query, if I want to write a query, so I'm now writing a query. Is their uh, modifier, or yeah, modifier before me? Right. So I can write this query, and then so these are my keys. Okay. So the key basically, so key are every number. So keys are every word. Sorry, every word is a key, but we can say that of those keys, my creature and forest, right? So they basically mention that okay, fine. So yes, I have a modifier, and creature says I have a modifier, forest says I have a modifier, and then they will return the value. Yeah, the modifier value is fluffy blue and then verdant, right? So in terms of a sentence, you can also say that this is how you can verdant. Okay. So these are an example. So I gave you an example of a database, and you can have an example of a is within a sentence. Okay. So within a sentence, this is how your modifier can work. Okay. Okay. So I think there's a lot of stuffs right now to digest. Um, you guys can keep looking at these videos, work on your own, and I will also keep posting some. I did post this thing, the RNN, but I will also give you some introduction to that through my videos a little bit later on over the week. Okay, so thanks for joining, and I hope you like it, this lecture, and yeah, keep learning, keep learning. So that's all I can say. And have a nice weekend, guys. So Vishal, I think we are good for today's yeah,
Okay.
topic.
Okay, then take care. Bye.